I started here, right? So this is my chapter 3. Chapter 3 is called Consumption and Saving because this is exactly like what this is about, right? So this is the economic content. But it's like this chapter is a lot about showing you how to optimize over time, right? So the main thing that I'm going to show you is this what we call intertemporal optimization. Right? And that's basically where we started off last week. So we stopped here, right? So what I showed you already last week, and I mean this just directly follows from the solo model, right? So I mean you may remember that I said the solo model is important, so here it already shows up again, right? Because basically what I want to do, I want to take the solo model, and the only thing that I want to do now is to replace the consumption equation by something that we would call microprofit, right? So basically I want to give you an example of that. The problem is with consumption and saving, this becomes immediately intertemporal, dynamic, right? Because saving is something where obviously, right, it matters for the future, right? So that's why this is immediately dynamic, and this is where we will need everything else. So yeah, we started here. So basically, last week I said this equation here is important. This is actually nothing very fancy, so let's say you don't need many maybe assumptions to get here, right? So really what this equation just is really just combining basically our economic identity that tells you output in your economy equals consumption plus investment, right? Which is really just accounting. And we're using our neoclassical production function here, let's say Cobb-Douglas, right? Whatever it will be Cobb-Douglas at some point, but it's just a production function, right? And what we're using is these capital dynamics, right? So this law of motion for capital, or like is really this idea, right? If you have a capital stock, you can also use it in the future. There is a certain share of capital that depreciates, that's this delta plus the new capital that you're creating by investing. Right? That's really just the only two things that we need now. You combine this and then you get this equation here, and basically the only difference compared to what I did in the solar model is now that I'm writing that in terms of consumption, because that's where we want to go, right? We want to think about consumption. So the interpretation is really just the same, right? So what you can consume in any given period t is what you produce minus what you invest, right? I mean, basically this term over there is just the negative of investment, right? So this here is just equal to IT. But the reason why I replaced IT is that I wanted to show you that investment in this economy also just depends on the capital stock, right? So the point of equation 1 basically is to show you that if you want to talk about consumption, all we need to know is capital, right? And this is where I said, like this model, I mean, this will become the neoclassical growth model at some point. This is all about these capital dynamics, and here you can already see this. Okay, so the example that I typically give is, let's say you know what K0 is, right? If you know what K0 is, and you know, basically you have any idea how households set C0, then you can also compute K1. And then, if you again know how a household set C1, you can compute K2, and you can do this up to the infinite future. And then you basically know how your economy is like behaving, right? So then you're done. But the question is, what is this rule how household set C, right? And this is exactly what we're looking for. And kind of I hope maybe intuitive example was, this is where we stopped last week, when I said, okay, let's now consider a household that's very short-sighted, right? He or she only thinks about current consumption, right? So what would that household do? What would that person do? Well, that person would basically say, what we said last week, right? They would set the future capital stock to 0, right? So that person would say, okay, I don't care about the future, so why should I keep capital, right, to produce in the future? I just said k t plus 1 equal to 0. It's t, sorry, right? And then in period t, I can consume everything, right? I can consume the current level of production, plus I can actually eat the remainder of my capital stock too, right? So basically, dissave, disinvest, whatever you want to call this, right? And then I have maximum consumption, maximum utility today, but like from the next period onwards, there's nothing left, right? So that's also what we said. So that implies that this economy would be a very short one, right? You would have consumption period 0, and afterwards everything is just 0, right? No capital, no production, no consumption left, about 0. Okay, this is where we start. So then, I mean, this is why I showed you this example, right? To basically make a point. It could be that maybe some people behave in a way, but maybe not everybody, right? Some people may actually think about the future too, right? So this is kind of the most extreme case, right? So now I want to give you like the more general case, in that sense, to assume that households care not only about today, but they also care about the future. And now I will show you how we put this like formally in our maximization problem, right? So what does that mean? So we say we're defining here, we call this a value, right? The value of current and future consumption in the current period, so in period 0. So what is that? And that is in the end just the sum of all future, and I mean now I'm already using the term utility, right? So that's one difference, right? From here I was just talking about consumption. I mean, typically we say I don't care about consumption, I care about utility out of consumption, right? So I'm doing that here, I'm introducing a utility function, right? And then we're just thinking about the sum of all future utility streams out of consumption here in all future periods. Right? So, I mean, intuitively speaking, what I'm doing is really just saying, instead of just looking at the CT, we look at your utility from CT, but also CT plus 1, CT plus 2, CT plus 3, up to CT plus 100, plus 1000, up to infinity, right? And it's in the sense, I hope, kind of simple, right? Only what we do is just to sum this all up. Right? I mean, I'm just using a summing sign here because by writing this up to infinity, you don't want to do this, right? But this is really just the idea. We're just summing that. Right? So now there's maybe one more thing I should say, right? I just said we're just summing. It's actually not true, right? There's this beta showing up. So we are summing, but we're weighting somehow. So let me try to give you an example of what this beta is doing, right? So if I write this sum here, say I write this in single terms, right? So I say we start off with t equal to 0. So then we would have beta to the 0 times u utility of c0, right? What is beta to the 0? 1, right? So this term would just be equal to 1. Now we go to, this was for t equal to 0, right? So now we go to t equal to 1. So what do we get? We get beta to the 1 plus u of c1. Right? What happens in period 2? We get it, for t equal to 2, we get it beta to the 2 times u of c2. And so on and so forth, right? And this continues. Why do I do this? Well, what this is doing is beta here. I mean, you have it on the slide, right? This beta here is a number which is between 0 and 1, which means if you take these exponents here, right? Beta to the 1, beta to the 2, beta to the 3, what happens with a number which is between 0 and 1? Gets smaller and smaller, right? So just, I mean, compute that for yourself, right? I'm going to take 0.5, from 0.5 to the 2, 0.5 to the 3. This thing will converge to 0 at some point, right? And this is true for any number between 0 and 1, right? So a typical number that you see for such a beta would be like 0.9 or 0.99, but even then, these things converge to 0. So what we do here is what we call discounting, right? So if this means that like this utility that we get from current consumption, this gets the full weight, right? This is equal to 1. Consumption or utility from consumption in the next period, well, it gets a weight which is a bit lower, right? Let's say 0.9. But then this is actually growing like smaller and smaller over time. Right? So this means we care about the future, but we always care about like every future period, the further it away, you care a little less, right? This is just a simple, I think it's a very simple idea actually, right? And this is why we have this beta to the t showing up here. Right? You can think about this as weighting this future utility. Which also means, I mean, like in principle, we're like summing up to infinity, right? But at some point, this thing here will approach zero, right? At least in the limit. So this is where there's an anti. Okay, so this is our discount factor. What you have here on the slide is that I'm also introducing the discount rate. Maybe you've seen a discount rate if you take a finance class. People typically think more about these rates. So I always find these factors a bit easier. In the end, the one is just equal to 1 over 1 minus the other, right? So, I mean, these things match. So maybe to give you the interpretation of the rate, right? So if you set beta to 0.99, let's say, and now if you take your calculator, what that would mean for theta, that would give you a discount rate around 1%, right? So you would be saying, basically, you would be discounting from, and also on your frequency, but let's say from year to year by about 1%, which you could think of like, if this is the average return in your economy, this would kind of like correspond to each other. We'll actually see this, right? This is exactly the idea, right? Yeah, so this is like the average rate of return in your economy, right? Okay, this is what this beta is doing. I haven't talked about the utility function yet, just except now we used to use a utility function. What is these two things here? U prime larger than 0 and U double prime smaller than 0. Utility in this case, exactly, right? So this is this typical idea that we basically put in everywhere. I mean, we already talked about that in terms of the consumption function, right? But also here, right? If you increase utility, consumption, right? You basically have this form, right? So it's always better to consume more, but if I'm already consuming a lot, the marginal benefit, the marginal utility from consuming even more becomes smaller and smaller. It's positive, but it becomes smaller and smaller, right? So these typical things we're also important to understand. Okay. And maybe the last thing to point out, because this is something that we will change at some point. So how this is written here, I'm basically assuming that there's perfect information, right? So I'm basically saying that household knows exactly what will be future consumption. Kind of a heroic assumption, obviously, right? Nobody knows what's happening tomorrow, right? But here we start off with this perfect information, right? So I'm going to make it say we have perfect information about income, and this is why there's also no uncertainty about consumption in the future. We will change this in chapter 5, I think, right? Which then means that we will be introducing expectations, for example, right? But so far there's no expectations here, there's just full knowledge, right? This is what we call an intertemporal optimization. This is an intertemporal household problem that I'll show you here. So this is the thing that we want to work with, right? And maybe, I mean, this is basically now providing micro foundations. Right? So this is kind of what I mean by micro foundations, because what we do here now is to really think about what would a single household do, how would he or she set consumption and saving, right, which is kind of the other decision here we have to make, right, in terms of capital, in all future periods. And we're deriving that, and I mean, that would be like the Lucas way of saying that, we're deriving that here from the fundamentals, from the preferences of the household. Right? So we are not just, right, maybe to give you that example again, right? I mean, in solo, we just said consumption was equal to like this share S of output, right? Which is, there was this constant share S, right? We just basically said NT, right? So consumption every period T was just equal to YT, right? Here, we're doing something fundamentally different, right? I mean, so far I'm not even giving you what consumption is, right? We're still looking for that. But this is basically what defines it later, where it comes out. And this is what we call a, so this was the solo, right? Just to make sure that this is not what we're doing, right? So this is what we call a household problem, right? Because, I mean, so far it is a problem and we still have to solve it, right? We haven't done that yet. Okay, but this defines it. Maybe 2 or 3 more words about this infinite time horizon, because I know that this is sometimes difficult for people to say, why do this? Why infinity? I mean, first of all, in principle, you don't need infinity, right? I mean, you can write the same thing here and just say we are maximizing up to a period capital T, which would be 100 or maybe 10, whatever you think how long people live, right? I mean, that's something you can do. And this is actually what we do in our so-called overlapping generation models, right? It's what we call OLGs. In an OLG model, you have exactly that idea, right? People live just for an ending period of time. Surprise, surprise. I mean, that's obviously what happens, right? And you can also model this, right? And I mean, basically then exactly what you get is you would have people in terms of like, actually like years, how long do you live, right? So then if you look at these models, people actually really model, I don't know, 80 years or maybe 100, however you think about it, on average like 80 years, right? And this is how people make their maximization decisions. But the important thing is, I mean, even though like maybe I die, but typically the world doesn't, right? Because then there's other people basically continuing to live, right? And this is exactly what these overlapping generations do, right? It's with these models, it's really about one generation just dies, and then there's a new generation coming up, and you can really look at how these interact, right? So this is basically an own branch in, I mean, this is in the end, these models are very similar, right? They would start exactly like this, just have like not this infinity here. So like in terms of the techniques, you can basically use exactly the techniques that I show you here to do this. They sometimes imply some interesting stuff, yeah, this is basically for future macro adventures if you want to do this. So this is something you can do too. But still, I mean, we basically start off with this infinite horizon, and I mean, this you can make an argument in the sense of like, okay, maybe people are altruistic in the sense that maybe I die, but I care about the next generations. You could think I care about my kids, right? So I mean, you could say this is like a bequest motive, right? So even though I know I die, it could be that I actually want to give something to like my children, right? So this could basically motivate that. But there's also like, and to me, this is actually the bigger argument, to be honest. It's just like a way out of I mean, these models become difficult anyhow, and you always have to question, where does it make sense to make stuff difficult, or where does it make sense to maybe keep stuff simpler, right? And it turns out that if you have these infinite horizons, this is one big advantage, because it implies that it does not matter, let's say, for how long I still have, right? Do I expect to live just 10 more years, or do I expect to live 50 more years, right? This is exactly what happens in an OLG, right? In an OLG, people will behave differently conditional on that. In these models, they do not, right? Which means all people behave always the same, and that basically makes the whole stuff a bit easier, right? And this is why we typically start that way. Right? So what I'm going to say is that, like, time in these models doesn't really matter, right? So we're basically always at the same point in time, right? Because people always live forever, and then it doesn't really matter, right? Okay, good. But let's say, for example, I mean, if I work with OLGs, if you want to talk about demographics, for example, right, demographic change, these OLGs are basically the thing to do, right? Because then you can actually really model these different cohorts, and maybe like older people, like older cohorts growing. What does that do, right? Because these people save differently. So this is exactly what you do with these kind of models. Okay. So this is already just to explain a bit why we do this. Good. So this is what we want to maximize, right? I mean, I just put that here in words, so you will at some point see that we typically write, we are maximizing this thing, right? And I mean, maximizing is nice, but this here would be very easy if you would not be constrained, right? I mean, then you would just always consume infinity, right? That would be great, but I mean, here we're facing constraints, right? And the constraint that we're facing is here. So here I'm really just repeating the one that I gave you like 4 slides earlier, right? It's basically just again the story, right? You cannot consume more than what you produce minus what you want to invest, right? This is, I mean, this could call this resource constraint, technology constraint. I mean, this is all that there is, right? So this is constraining these household maximization problems. And maybe one thing to notice, I mean, here I'm writing this like from t equal to 0 up to infinity, right? So this here is really this very long sum, right, over all these utility streams. Here, I'm just writing this in terms of general t and t plus 1. So, but this thing here has to hold, and then let's see this on the slide, it has to hold in every period t, right? So this thing always has to hold. It has to hold a period t equal to 0, t equal to 1, 2, 3, 4, 5, up to infinity, right? There's no way around this constraint. Right? So, but what people can do, and I mean, that's basically all this is about, right? I mean, this here is production, this here is investment. So people will think about basically how to allocate consumption, right? How much to consume, how much to invest in every t, right? That's the choice that they have to make. And they make their choice based on this.
You're speaking about investment all the time, but in the dinosaur model, it's the saving rate, right? So is there just a linguistic difference, or is there like a...
Well, I mean, in these models, what is true is saving equals investment, right? So I mean, this is a model about goods, right? I mean, this is always very important when everyone talks about this, right? This is a model about goods. This is not a model about money, financial markets, whatever, right? So if you talk about saving here, what I mean by saving is basically is invested. So in a way, it is linguistic, right? And saving just means out of what we have produced, we are not eating all of this. And this by construction, and this basically falls out of this accounting, is equal to the investment then, because none of these goods, I mean, you will not just throw it away, right? But it will basically go directly into the capital. So in these kind of models, in terms of, this is always important to say, this is real saving, right? So what I mean by saving here is really, I'm basically storing goods, right? I'm not eating them, but we're storing them from one period to the next, right? And if we do this, this is investment. All right, so this is what we have to solve, right? And I mean, this is now what we mean by intertemporal optimization, right? And let me start, or dynamic optimization, right? So let me start again with the 2-period version, right? Remember this example that I gave you at the beginning, right? These biotic households. This is a bit similar. Now I'm basically doing what I just talked about. Just say, instead of having this infinite horizon, we just say we have an household that knows, right? I just have 2 periods, right? I'm born, I inherit a capital stock, right? I start with a capital stock K0, and then I live for 2 periods. And I have to decide how to allocate this capital stock basically across these 2 periods for production, right? And what to consume. And this is what you get, right? And this looks already, I think, pretty much more doable, right? So the first part here should remind you of this infinite sum that I gave you at the beginning, right? So here we're just maximizing utility in period 0, u of c0, plus discounted utility term, right? And given that this household dies after period 1, there's no C2, no C3, whatever, right? This is all just 0, right? I don't care about this, right? And now, and that's the big advantage, right? We just have 2 periods, so we just have to think about 2 constraints. Right? The first one for period 0, and the second one for period 1. Right? But note that they are different. This is kind of what I said on the earlier slide, right? So this one here in period 0, this is exactly the equation that I gave you here. The only difference being that I'm just now using 0 and 1 instead of t and t plus 1, right? So here we have consumption period 0 equals production minus investment. Right? In period C1, this is slightly different because in period C1, I know I will not be around anymore tomorrow, right? So what I do, I behave exactly like this myopic household that I gave you at the beginning. I eat all my capital stock, right? So there's no point in saving or investing, right? So I will not keep any capital stock. So what we do here is that we're basically setting K2 equal to 0, right? That's just spawning out of this 2 periods. That's what you have, right? So this is basically this it is already a dynamic optimization thing, right? Because we have to think about these 2 periods. But it looks, I think, much more doable, right, compared to the setting with this infinite sum and so on. So I want to show you this here first. And actually, then doing the other stuff turns out to be very similar. Okay, so maybe just to like point out the trade-off once more, right? So I mean, again, I'm waking up. I'm inheriting a capital stock here. So then basically what I have to do, I think about, okay, I give the capital stock to the firms in my economy, they will produce with this in period 0, right? This is basically what happens here. And then I can buy these goods, and then I'm the household, right? Then I have to decide how much of these goods that my firms have produced, how much do I consume, how much do I save, and by that invest, right? Or in different words saying, how much do I keep for the future, right, of these goods that were produced, right? And this then determines my future capital stock, right? This then determines my K1, which is showing up here, and by that determines future production, right? So the trade-off is, the more I save, the more I invest, the more can I consume tomorrow. But obviously, if I save more, I can consume less today, right? That's just a very simple trade-off that we're basically formalizing, right? And that's what's happening here. Okay. Good. So there it is. How do we do this? We set up a Lagrangian. And here it's, I think, hopefully doable, right? So what we do, I mean, set up your Lagrangian function. This is what we want to maximize, right? So this is our objective. This is the utility in period 0, and in period 1, discounting with beta. Again, maximization would be boring, right, if there were no constraints. And the thing here is there are 2 constraints, right? So the first one is this constraint in period 0, which is just this here, right? And the second one is this constraint in period 1. Sorry, which is just this one. Right? And I mean, what do you do in a Lagrangian? Where's it now? There. What you do in a Lagrangian is you give these, right? You weigh this, if you want, these constraints with these Lagrangian multipliers, right? And I mean, the point here is, given that there's 2 constraints, there's now also 2 multipliers, right? I'm pretty sure you've seen, like in your undergraduate, you've probably seen many Lagrangian type of problems, right? Because this is typically what we do if we optimize. I mean, that's what you do in micro, that's what you do in macro, right? But the standard setting typically starts with the 1 constraint. Right? Now we have 2. And the next thing is we not only have 2, but it's actually the one matters in period 1 and the other one matters in period 2. But it turns out, and this is basically what I want to show you here, in terms of doing the maximization, right? So in terms of doing the math, you actually don't have to care much about this, right? It's maximization with 2 constraints. That's what it is. Okay, so this is how you set up the Lagrangian. How do you solve the Lagrangian? Do the first order condition. Exactly, right? So what you do for first-order conditions, you think about what variables, right? So I think of me as being this household, right? So I have this capital stock, and now I need to think about how much to consume, how much to save. So what I do basically, I take these first-order conditions, so I do derivatives, right, of this Lagrangian with respect to all variables that I have to decide upon, right? So I, the household, have to decide upon my current consumption, my future consumption, and the capital stock in the next period, right? Because K0 is given. About K0, there's no discussion, right? But these are the three things that we have to decide about. Right? And there's, I mean, with each of these decisions, there's a trade-off involved, right? If I consume more today, I will get utility today. This is nice. But this will mean I'm consuming less tomorrow, right? And I mean, this is a global thing, but what this Lagrangian is allowing us to put this in numbers, to put this in equations, and basically to weigh the one against the other, right? So this is exactly what we want to do. So yeah, I mean, you have the first order condition here on the slide. It's actually dead. Let me see why. I've used this slide for ages, but I'm just seeing that now. Right? There should be more need to. Right? Okay, that's better. So yeah, this is the first order conditions, right? And I mean, it's just take the derivative, right? So for the first one, take the derivative of this thing here with respect to C0, right? I mean, the important thing is really don't be confused by these numbers or by these terms becoming long and involving many variables. It's really just like do what you're supposed to do, which is in this case, if you do the derivative with respect to C0, just see where is C0 showing up. So do the derivatives one after the other. So with C0, where's the C0? There's one here, and there's one here, right? So what you do, what's the derivative of this guy here? I mean, you have it here. It's the utility, right? The first derivative of the utility function, u prime c, right? So the marginal utility. There's no C0 here, but there's the C0 here, right? But this is basically just like the variable per se, and the variable is multiplied with our Lagrangian multiplier, lambda 0. So you get here this minus lambda 0. In all the other terms, no C0, so that means with the first order condition, you're already done, right? So this here comes from here, right? And as we said, right, set that equal to. This is the month, right? Actually, this equation 4 already tells something, right? So you can rewrite this and say, okay, that means this lambda 0 equals u prime c, right? It's just rearranging that. So what's the interpretation of lambda 0? Exactly, that's what you have here on the right hand side, right? It's like in terms of the Lagrange, right? How do we interpret these numbers in a Lagrange? I know that Maria has just uploaded you this nice thing, that's why I'm asking. I mean, she's explaining that very nicely there, right? That's these shadow values, right? Yes, or now it's.
Yeah, I wasn't really sure if it is if I was applied correctly, but shadow prices are like the amount I have to pay in order to get like one additional utility.
Yeah, exactly. I would here frame it from a bit from the other direction, but it's exactly that, right? So here I would say lambda 0 is right. This is your objective, right? And your objective is measured in utility terms, right? And lambda 0 is always how much do you gain in terms of your objective, here in terms of utility, if you relax this constraint, right? So the constraint which is attached to lambda 0 by 1 unit. Right? And And what you get here is the marginal utility of consumption, because that's exactly, if you allow me to consume one more unit, this is what I get. Right? So in a way, it's natural that this here it's out, but that's exactly what you get. Right? Okay, so this is this lambda 0. This is the first order condition. So now you also do it with C1, right? So this is basically, how do I optimally set my consumption in period 0, right? How do I optimally set my consumption in period 1? For that, I look at this derivative here. And I mean, for that, I just do the same thing, right? So where's C1 showing up? Right, there's a C1 here, and there is a C1 here. Sorry, now I have too many things here. At some point, you will not see anything anymore. Right? So if you do the derivative with respect to C1, what you get here is just beta times U prime C of 1, right, at C1, minus the lambda 1 from here. Right? Looks very similar to the first one. The only difference is you have the beta here showing up. So if you rearrange that, this is exactly what you get, right? Lambda 1 equals beta times U prime C. So if you relax this constraint in t plus 1, that's the marginal utility that you get. But I'm discounting that because that just happens in the future. This is where you multiply that with beta. Maybe a bit more complicated is the last one, right? So this here is basically exactly what you always do, right? It gets a bit more involved with this last first order condition. Let me show you why. Now we have to do the derivative with respect to the capital stock in the next period. Right? And I mean, just intuitively, the problem with the capital stock is exactly that it has this dynamic property, right? So if I want to have a higher K1, I want to have higher capital tomorrow, I have to save more today, so that restricts my consumption today, right? So this is exactly what this equation will show, right? So if you do the derivative with respect to K1, technically what you have to do is you look, where is K1 showing up, right? So there's first of all a K1 here, right? And I mean, this here is again pretty simple, I guess, right? Do the derivative, minus lambda 0 times K1, you get a minus lambda 0 here, that's the first term. But now you could go, there's a K1 here, right? So that's the second term. We have here this lambda 1 minus lambda 1 minus f, the production function, right, at K1. We need the derivative, this is f prime with respect to K, multiplied with lambda 1, we get a plus because of the minus and minus, right? So this is the second term, right? This comes from here. And there's the last term, which is just here, right? Which is this minus 1 minus delta K1. You get here, again, plus lambda 1, because you have the minus and minus here. And that's the term. So this one looks a bit more ugly, right? But it's in principle doing the same thing. The only difference is now, right, K1 shows up in both constraints. And that's the mathematical way of saying, if you want to have a higher capital stock tomorrow, it already shows up in your constraint today, right? And this is why here you get the lambda 0 and the lambda 1 in the same first order condition.
Why do we leave the L out when we take the derivative of the production function with respect to K in equation 6? Because I mean, without knowing the form of the function, we wouldn't possibly have to take it with, but that's just a notation thing.
What do you mean?
Well, we take it with f prime of K, which is lambda 1, right?
Yeah.
And in the production function.
Because I'm dropping the L here.
Yeah.
Ah, okay, got it. Yeah, it's basically just to keep it simpler.
Okay.
You could, maybe the L should even be there. Yeah, it's just like me trying to make that a bit smaller here, but it's, I mean, it's, yeah, actually the L should be there too. All right. Yeah, one more thing, and then we have to break because then you can think about it. Maybe that helps. So I mean, these equations is just equations, right? I mean, I tried to give you a bit of interpretation already, but obviously you can make that look nicer to get an interpretation. So what we do now is to say, okay, I have these two conditions here, and what you can now nicely do, I mean, here you have these lambdas, right? And I mean, we can give this interpretation to the lambda, we just discussed that, but in terms of the equation, it's not really helpful, right? So let's replace these lambdas by these two terms. Right, so it's really just all I do is insert that in equation 6. Put this in here and put this in here, right? And then you rearrange a bit, and then you get this guy. Right? So it's a bit unfortunate to have that on the next slide, but really, right, for the lambda 0, what you get is the u prime C0, and for the lambda 1, what you get here is the beta u prime at C1. Right? And now again, go here and see that this is exactly this equation. And this is what we call our Euler equation. Right? Who of you has heard of this Euler equation before? Right? It's basically the thing that always calls out if you do a dynamic or dynamic household problem. Talking about this, also what this means in terms of economics, but it's like really the, I mean, you have it right, the fundamental equation that shows up whenever you do intertemporal consumption problems, right? And basically, like in modern macro models, every consumption problem, every household problem is a dynamic one, right? So this is like why the Euler equation will show up in basically every model you can think of. This is also why I chose to show you this here first in our chapter 3, because it's basically really important, like, and will like be one of these ingredients that from some point onwards you will just be using it, right? But you have to understand first where it comes from. Right? And I mean, maybe remember, I just showed you this here, like from this 2-period thing, right? And I mean, here you basically get the same equation. I will show you that on the next slide. And for the like full intertemporal thing. But the equation in the end looks basically exactly the same, right? So whenever I'm talking about an Euler equation, or when macroeconomists talk about an Euler equation, this is what we mean. Okay, good. We talk about the interpretation maybe next, but yeah, go ahead.
Yeah, is there a reason why the 1 is suddenly in front of the k?
Yeah, that's true. I rearranged that here a bit. The reason is that so what we typically call this here later, it's actually here on the next slide. This looks like a gross return on capital, right? So basically what this here is, we typically call this R later, right? It's F prime K is the marginal product of capital, right? So if you save, you get an additional unit, if you invest, right? You get an additional unit of capital. And this is the output that you create from that additional unit. Right? So it's the return on investment. But we are deducting here the depreciation rate because of your capital stock on every period a certain share is gone. Right? So this is why this here is like the gross return on investment saving. Right? So the gross return on capital, if you want. Right? So that's why we're rewriting this, because it just like looks more nicely.
Because for each unit that you invest, you get first the same unit back, and then its marginal return, and then the cost of investing, which is basically the depreciation in the current period, right? Which is the delta, right?
Yeah, exactly, right? I mean, exactly, right? You have the capital stock. I have a certain set of machines, right? And I mean, that machines I'm using in a certain period to produce, right? But then in the next period, I first of all can use these machines again, that's the one, right? And then I have additional machines, those that come out of the capital stock that I invested, F prime K. And of these machines that we were using last period, a certain share doesn't work anymore, so we have to throw it away, that's depreciation, that's the delta. Right? But the one really is there because of the capital stock that you have. In principle, you can use it again. Right? And this is why the one is there. So let's do some break first, and then we go back here and talk more about it. Right. Yes.
Skippen wir auch mal vor, würde ich sagen.
Und zwar, wir nehmen aber das Kind auf den Brust, wir nehmen die Schulter und das liegt hier dreimal. Einmal liegt hier, dann die Schulter. Und dann üben wir so überlegen, dreimal zur rechten. Und wieder nach links, einmal liegen, hoch, liegen. Und nochmal auf der anderen Seite. 1, 2, 3. Einmal noch auf jeder Schulter. Und dann wieder zur Mitte ausrichten, dann kommen die einmal Arme angewinkelt, einmal fürs Gesicht, die Handflächen zeigen zu uns. Und dann strecken wir die Arme nach oben und drehen, bis die Handflächen nach vorne zeigen. Genau, und wieder zurück in die Ausgangsposition und dann einmal kräftig nach oben strecken. Wieder einklappen und hoch. Genau. Und dann machen wir noch 3, 2, 1. Sehr gut, schütteln dann die Arme aus. Wir brauchen ein ganz bisschen Platz, so ist auf Schulterhöhe. Und zwar machen wir noch folgendes: Ich drücke um, wir nehmen einen Arm über den Kopf und einen an den Rücken und dann wechseln wir. Wir halten nicht fest, sondern wir machen das dynamisch. Genau, wir versuchen immer einmal höher zu kommen als beim letzten Mal. Wir hintereinander auf den Rücken anzunehmen. Ja, die Schmalfahrt kommt immer ein bisschen näher. Ihr merkt bestimmt, eine Seite ist schlechter als die andere. Das ist die, wo man das selber machen müsste.
Das geht gar nicht.
Genau, wir machen noch zweimal. Sehr gut, und schütteln dann die Arme locker aus. Dann kommen die nochmal über Kopf und dann gehen wir alle nach links. Erstmal alle nach links, diese Seitenneigung, alle nach links. Ja, links, genau. Links ist nicht da, wo ich bin, sondern die andere Seite, genau. Dann nicht noch das Spiegelverkehr. Und wieder links und dann rechts. Ja. Links.
Ich glaube, die hast du nicht so raus. Ich weiß nicht, was das ist.
Einmal zu jeder Seite, einmal noch schön in die Länge ziehen. Und die Arme wieder absenken. Die machen wir dann mit der Brust nochmal zusammen. Wir strengen uns einmal kurz an. Wir pressen mal so fest. Wir können zusammen ganz fest machen, alles und dann locker. Ja, und wir pressen nochmal. Da spannen wir alles an und dann ganz bewusst alles zu entspannen. Genau. Und nochmal anspannen, halten. Noch ein bisschen locker lassen. Zweimal noch. Nochmal einmal powern. Genau, richtig doll festdrücken und loslassen. Und letztes Mal. Nochmal alles anspannen und ganz bewusst entspannen. Genau, sehr schön. Wir sind schon bei der letzten Übung und zwar ist das der Baum. Wenn ihr Platz hier habt, sind wir ein bisschen
Ich glaube, den Baum schon wieder richtig gut. Ich glaube, da wirklich auch mal.
Einfach auf einem Bein stehen, das andere so kurz rumgerutscht. Steht auf einem Bein, legen die Handflächen aneinander. Suchen uns irgendwo einen Punkt, wuchten wir starren oder advanced, wir schließen die Augen. Ganz kleinen Moment zu entspannen. Irgendwas so runterzufahren. Oder stehen, ein Baum sein. Und alles wieder auseinandernehmen. Alles mal auslockern. Nach dem nächsten noch rein. Vielen Dank fürs Mitmachen.
Ja, so, aber. Baum, Digga.
Bạn Hà Nội sa là mình
So yeah, this is my Euler equation. As I said, it is important. So yeah, maybe just intuitively, right? What this equation is doing, it really like shows you this trade-off, right? How much do I consume today versus how much do I consume tomorrow, right? And this is just an equation that boils that down in what I just said earlier, right? If I consume more today, there's less tomorrow. And how much there is tomorrow, that will depend get the maximum utility conditional on your constraints, right? So that's the optimum, right? And I mean, that's basically what falls out of the Lagrangian maximization problem, right? So, okay, so we found basically an equation that describes the optimal behavior of the household. And it tells us, and I mean, this is the equality here, the household must be indifferent between consuming the marginal unit today, right? So that's the marginal utility of consuming today, that's the left-hand side. Or alternatively, investing this unit and consuming the return one period later, right? So this is the return that you then get one period later. We're weighting that in utility and we're discounting, right? Because we always care less about the future than we do about today. And that return that you get is exactly the term that we were just discussing. It's what we call this gross return on investing or saving, right? Which depends on what's your return on investing, right? So how much, if you gain more capital, how much output, if you have more capital, how much output can you actually create? That depends on your production function, that's the marginal product of capital. And it depends on, like, from period to period, how much of your capital stock do you have to throw away, right? Because that basically depreciates. That's the idea, right? It depreciates your capital stock over time. Okay, and I mean, this is why, say, economists like this equation so much, right? Because it really gives you a formal way to talk about this trade, right? How much do I consume today? How much do I consume tomorrow? And what's the decisions involved, right? And this summarizes all of that, right? And I mean, this is why we do this math, right? I mean, we're not doing this math because we are big fans of math. Maybe some of us are, I don't know. But to me, it's always like I want to find a way to think about these trade-offs. And this is, I think, to me, always a very, very good example of that. Okay. Good. So as I said, that was so far actually just the two-period version. Obviously, you want to make that more general, right? We want to go to this infinite horizon thing. So this is what I want to show you now, but it will actually turn out this is basically the same thing except for one little thing that you need to add, right? Okay, so now I make this the full household problem, right? In the sense of that we now have here this infinite sum again, right? So we are maximizing over all future periods. And how I'm writing that here, you see it is we're maximizing over consumption in all future periods, subject to, and now you have here this budget, I'm calling this a budget because it's actually the resource constraint, right? This resource constraint, and this thing has to hold in every period t, right? So I mean here, I wrote two equations, right? Here I'm basically saying this has to hold for every t, so this saves me to write this here infinitely many times, right? But in principle it should be there infinitely many times. Okay, good. So yeah, we're choosing consumption in each period, so we actually have an infinite number of choices, right? We have an infinite number of choices to make, we have an infinite number of constraints. That sounds very complicated. It's actually not that complicated, right? So that's exactly what I will show you. And I mean, this is kind of one of the big advantages, right, also of this Lagrangian, that you can just put this all in. It's really just the same thing, right? Okay, so here is the Lagrangian for the infinite horizon setting now, right? And this should look relatively familiar. The only thing that I did now is to have this infinite sum here at the beginning, right? So this here is still our objective, but note that because of the infinite sum, this is exactly this objective, like the sum of utility today, tomorrow, up to the infinite future, right? This is still there. So this first term is just this here, right? And here I'm adding actually all of this infinite number of constraints. So the major trick here is that this lambda here has a t index, right? So that's the major change to before. Here, I call this, sorry, where is it here? Here I call this lambda 0 and lambda 1, right? Now I'm saying you will get a lambda 0, lambda 1, lambda 2, lambda 3, lambda 4, right? All of them are there, right? I'm just writing this in this very compact way using this sum notation. But in principle, you have here this infinite number of constraints. The interpretation of this guy is exactly the same as we had before, right? This is still the shadow value just for every period t constraint, right? That's it. There's one little thing that I'm changing compared to before. You see that this beta t here is basically out of this big parenthesis, right? So what that does is basically, if you would like write this step by step, we are also multiplying the constraints or the lambdas here with beta to the t, right? Because there is this parenthesis here, right? So beta is also multiplying the constraint. I haven't done that before because basically economically you don't need this. You will see once you do the first order conditions that if I write it this way here, they look nicer. And it's actually easier to do this later, and this is the typical way how we write it. In the end, in terms of interpretation of the lambda, it really doesn't matter, right? Basically, the only thing that this is doing is that we are multiplying beta times lambda, and this is just scaling. And I mean, say the size of this multiplier, whether this thing is 0.5 or 0.53, nobody cares about that anyhow, right? How do I know how to scale this, right? So this is really not a thing. It's more like a convenience to write it that way. Okay. So the thing that you should see is I take all these constraints, put this in this infinite sum, right, in the Lagrangian, and add this t to the lambda, right? So this Lagrangian multiplier. So like in, let's say, the standard problem that you probably know from your undergraduate, you have one lambda, right? So in the two-period problem, I showed you two lambdas, so lambda 0 and lambda 1, lambda 1 and lambda 2, whatever, right? So now I'm showing you lambda t, which in this infinite sum implies that we actually have infinitely many lambdas. Okay, so far we can deal with this. So what do we do now? Well, we do the same thing as we did before. That is actually, once you know how to do it, it's pretty much like what you always do, right? So I mean, these first order conditions look very much as they did before, right? So I mean, just note here, this is the first one for CT, right? So maybe that's a difference, right? I mean, that's also why I started with the two-period version, right? In the two-period, you could basically say, let's start with period 0, we do C0, and then we do C1, we go step by step, right? Here, I'm basically doing all of that at the same time, right? So we just do one first order condition with respect to CT, right? But again, t goes from 0 to infinity. So this first order condition here also holds for every t. So one different way to say that is that this is actually an infinite number of first order conditions, right? It just looks much more compact, and that's kind of the big advantage here, right? Okay. But I mean, where this is coming from is you just take this here and do the derivative with respect to CT, you get the beta to the t u prime that falls out here, and you get the lambda t from here, multiplied with beta, and this is exactly what you have here, right? This is our first order condition. And I mean, now you can just do the same thing as we did before, and say, okay, this then implies that lambda t equals q prime c. And this is really just the same as what I showed you in the baseline before. which here showed up in the lambda 1. Right? And this is exactly what we have to take care of now, right? So basically you should think about this. This is for lambda t. Now go to period t plus 1. Then you get here a beta to the t plus 1 times lambda t plus 1. Sorry, t plus 1. You get a minus, you get a plus in front actually. You see that I made this just as I did it here. Yeah, exactly. Right? So that comes from here and here. And now I'm looking at this term, right? So I get the f prime k, kt plus 1, right? Did I add the L or not? I don't know. Here the L is actually there. Okay, fine. Right? So this is where this term comes from. And if you now look closely, right, there's another kt here, which again, right, if you go one period in the future, becomes the kt plus 1. So we also have to take into account this derivative here. Again, beta to the t minus lambda t, you have the minus 1 minus delta. So you just get this plus 1 minus delta, right, as you see here. So this is this plus 1 minus delta. And you should have parentheses here, right? Because both of these terms here are multiplied with lambda and beta.
Yeah, I was working on the exercise sheet where we were talking about the question before, and
there's no t plus 2 showing up, or t plus 3, right? And there's no infinite sum anymore in this equation 12, right? And this is kind of the big advantage. This is kind of what makes this look again later like a two-period problem, because this whole problem is always just deciding about t and t plus 1, right? So let's say about period today and tomorrow. I don't have to decide about today versus compared to in 100 years, but this is always just about today versus tomorrow. And the reason why this is happening is that basically all out of this capital process, right? I mean, what you invest today, this is what you have tomorrow, right? And then tomorrow you can adjust again, right? And this is basically why this is the only thing that matters here, t to t plus 1. And this is also what allowed me to show you this two-period problem first, right? And this is why these two things look so similar. Okay. So let me maybe show you the last one here. I mean, I'm like for completeness also showing the derivative with respect to lambda. We haven't done that before, right? But if you do it completely, you should actually do this too. You have it on the slide, right? So this like basically your resource constraint has to hold, right? This is what this thing here is saying. And this last thing, this is actually new, right? So this is the part where I meant here you actually have to add something. Right? So this equation 14, that guy did not show up. So this is something unique to an infinite horizon maximization problem. What this is what we call the transversality condition. It looks maybe ugly. Let me try to just give you the interpretation. So what's happening here is we go, like in time, we go towards infinity, right? So think about like very much in the future. And what this here is showing you is that the marginal value, in terms of consumption units, of the capital stock has to approach 0 at some point. In words, this just means we are imposing that it is never optimal for households in this economy to keep saving forever, right? So here it is in words actually, right? It's on the next slide, right? So we are basically, so mathematically speaking, right? So if you open a math textbook, I'm not saying you have to do this, right? But I mean, this is intertemporal optimization, right? So like what these books would talk about, what we're solving here now is a system of difference equations, right? I mean, I said that before, right? You have t and t plus 1. You were also just saying, right? These two periods, right? What matters today matters for tomorrow, right? And the other way around, right? So this is a difference equation, right? And like every math textbook will tell you, to solve these things, you need something where you start and something where you end, right? This is always the case with dynamic problems, otherwise you cannot solve them, right? So you need what we call an initial and determinal condition. The initial condition is always easy because in our models, we always say we start with a certain capital stock K0, right? We inherit something and set that to 0, but we start somewhere, right? Okay, that's relatively easy. This is what we will typically call later, I will get back there at some point, this is what we call our state variables. So this will actually become important if we will solve this formally. I'll show you that at some point. This will be our state variables, right? What we condition on. But to solve these dynamic things, you also need a terminal condition. And this is what this transversality thing is doing. You're really just like imposing, right? This is an additional condition that we put in, right? So we are imposing that it's not optimal to postpone consumption forever, right? So that's the economic interpretation. Mathematically, this is what we do, right? I mean, I'm just, to me, don't hinge on this, right? This is a mathematical condition. To me, what I want to get across is exactly this, right? You basically need to impose on your model that households will actually want to consume, right? But in a way, that's a natural. I mean, it makes sense, right? So I'm not really bothered by this assumption to say, right? But you need it formally to actually for maximization.
And which part of this equation drives the limit to converge to 0? Is it the beta to the power of t, which will converge to 0? Or is it
So far, I don't care. I mean, here it would, yes. would, right? It could also be that your capital stock approaches zero at some point, right? I'm actually not making any statement here, right? We are only saying that this year has to hold, but I mean, that's a simple answer, right? As long as your beta is smaller than 1, then this year will happen. Okay, so here it is now, right? So if you did this, you have this here, and now you do the same as we did before, right? Take this lambda t, insert that here. And again, it's a bit like, that's hopefully what I want you to learn, right? I mean, you have these t indices now flying around, right? And I guess this is probably new for most of you, right? Because this is this dynamic model now. So, but again, this thing here, this equation 11 holds for every t, right? So that means I can also write this for t plus 1. I can also write lambda t plus 1 equals u prime c in ct plus 1, right? Where is it? And then you can also insert that here, right? And this is basically exactly what we did before in the other two-period thing, but now it just looks a bit different. You have to understand that this here really holds for all t, right? You could also write equation 11 for lambda t plus 100, right? It has to hold in every t, right? And this is why you can nicely, again, write this first order condition here in this way, right? But this is exactly the same equation as I gave you from the two-period problem. The only difference being you have a t plus 1 here and a t here, where we had this, I think, 0 and 1, right, in the earlier two-period. And the interpretation is just the same as I gave you before, right? It's written just a bit differently. The left-hand side is the marginal benefit of saving, right? And the right-hand side is basically the marginal cost, right? So if I decide on to save more, I have to consume less, so this is what I have to give up, right? So you can also interpret this as marginal benefit, marginal cost, which is one of these very natural interpretations that we use, right, whenever we optimize. So this holds here too, right? So that's this, right? Okay. So yeah, this is now our rule for consumption, right? And maybe just to say that, right? I mean, I was basically starting by we want to replace this rule, right, that we proposed in the Solo model, where I said we use something like, this here should be investment, right, equals S times production, right? So that was this typical idea, right? So where we have this constant S, right? And I call this the saving rule. In the Solo, where I said this is exactly what we don't want to do anymore, right? This rule here has one big advantage, right? It really gives you this very clear equation for what is investment, and if you know what is investment, you would also know what is consumption, right? This thing here is in a way much more ugly, right? Because this here does not say CT equals whatever, right? So this is not an equation where you can say CT equals something, right? It's just not there, right? But what this equation is doing, it is actually describing a path for consumption because it's always relating CT to CT plus 1, right? So it's more about the dynamics. Does not mean that we cannot get an explicit solution. Maria will also show you some, because if you assume a certain utility function and whatever, you can actually do this. But it does not fall out from the model per se. But let me show you some things that do fall out from the model, so or from the equation. Right? So the first thing that I always want to point out is if you see this equation, right, it basically tells you that consumption tomorrow depends on consumption today. It also tells you something about these marginal utilities, right? And I mean, remember this consumption function that I showed you. You know something about the risk aversion. Maria has talked about this too, right? So this equation very clearly states why we will see that consumption does not fluctuate much over time. Because it just shows you this, right? People don't like this. If I were consuming a lot yesterday, I also want to consume a lot today, right? I don't like fluctuations in consumption. This is exactly what this equation gives us. Right? And I mean, it falls out of this utility function as a result of this risk aversion. Right? And this is a way exactly one reason to think about this. You can think about what would happen if we made our agents, our households here in this model more impatient, right? And that's actually a way to think about this beta coefficient, right? So beta was like how much weight do I put on the future? If we decrease beta, right? So we lower beta, what this would be doing, right? You decrease the beta here. What does that do to this guy here on the right-hand side? What does that do to your current level of consumption? So let's say the beta goes to 0.1 or whatever. Yeah.
My current level of consumption also reduced because I already consumed more yesterday. And
Yeah, exactly. Yeah. I mean, I was thinking about the other way around, but yeah, you're right? But I mean, just looking at the equation, right? If you reduce the left-hand side, the right-hand side has to fall too, right? Otherwise, this thing here would not be equal, right? How do you decrease the marginal utility of consumption? You consume more, right? So that's the story. If I'm already consuming a lot, the marginal benefit of consuming even more goes down. So if you reduce beta, households will consume more today. That's exactly what you just said, right? You just said yesterday, but they consume more today and less tomorrow. And this is exactly what we mean by impatience, right? I mean, this is just what happens here, right? And the last thing, which is important here, is this R guy. And I mean, this is basically what you were like already going at earlier, right? The return on investment, the return on saving is crucial here for how much I consume and how much I save. And this is the major difference to the solo, right? In solo, people were saving irrespective of whether they actually got a return on that or not. They totally didn't care, right? Here they care. And this is exactly this R gap, right? So basically the return on saving matters. This thing is obviously a bit difficult because in a general equilibrium model, this thing will be endogenous. Right? And let me nevertheless use, I just have a couple of more minutes, but I want to give you this example here shortly, right? To give you some intuition what is actually going on in this model. And I mean, here I'm just, again, this is just the household side, right? In a way, this is still very small. We haven't talked about firms or anything, right? We're just looking into households here. But I want to show you some of the things that are already going on here. Already the model is that small, right? So to make it a bit more concrete, let's take a utility function. I'm just using this form here because it makes stuff look nice, right? So this will be my utility function. If you take the marginal utility, right? If you compute u prime, this is what you get, right? So just to give you that once, right? If you take this utility function u prime of Ct will just be the Ct to the minus sigma, right? And this is why you have this term showing up here, and this is the u prime Ct plus 1, right? Showing up here on the left-hand side, right? So this is where this equation is coming from. I'm really just taking this here, but for u prime, I'm inserting what I'm actually taking as my utility function, right? Why do we use this utility function? Because it now really allows us to think about the change in consumption, right? Because this now has this nice form with the C to the minus sigma, we can solve this for Ct plus 1 over Ct, right? Which then just depends on these guys. Right? And now you can actually really talk a bit about what a change in the return on saving, in my R guy here, is doing. Right? So what happens if you increase R? Right? The right-hand side of the equation goes up. So what should happen is also the left-hand side of the equation should go up. So if, right, I'm still this household, I'm deciding about how much to save, how much to consume, I see now the return on saving going up. So what do? I increase my consumption growth, which basically means I'm consuming more tomorrow. Right? This is this here, right? Households will increase consumption growth, Ct plus 1 over Ct. This is what in a micro class you would call substitution. Right? This isn't substitution effect, right? You basically increase consuming today, this is why I consume less today, but consume more tomorrow, right? Very standard micro problem, right? But this is happening here, and this is why I want to point this out, right? This is what micro foundations imply, lots of micro. So we're increasing future consumption. Does that imply that consumption today goes down? And there, unfortunately, the answer is that depends. Right? And it depends on the other thing that you've probably heard about in the micro class. So whenever you change prices, right, and the real interest rate is nothing else than the price of inflation. If you change the price, you get a substitution effect. That's this one. And you get an income effect, right? So if I pay you more for saving, you will save more, but that increases your income in all future periods. And that implies that you can also consume more tomorrow. You can consume already more today. Right? And then, depending on how strong the income and the substitution effect are, you will either do this today or you will put everything into the future. And then, in the end, depend on your risk aversion. Right? If you're very risk averse, you really don't like fluctuations in consumption, then you will not respond much to a change in the real interest rate. And you will basically keep your current level rather constant and will live that also in the future your consumption doesn't increase that much. If I'm very risk averse, maybe even risk loving, but you don't really need that. I'm not less risk averse, right? Then what I will do if I see that the interest rate goes up, I will actually reduce my current consumption with the benefit in mind that I can really benefit in the future by consuming more, but then I have to live with consumption fluctuation, right? So that depends on me what I want to do, right? And this is again a different way of saying this sigma parameter is very important, right? So it will really depend on these, and that's the Lucas way again, right? Your preferences. What do people actually want to do, right? Do they want to consume less or more, and how do they behave? And that all comes out of this income and substitution. Right? What we very often do in our models is to say we set sigma equal to 1. That will give you a log utility function. That's something that you see a lot. It's mathematically very clean. That's always nice. But it also has the property here that these two effects will exactly cancel in period 0, or CT, which means that the current consumption would stay constant, which is also sometimes nice, it depends, right? But this is all stuff which is going on here. Good. I mean, this is, again, part of this lecture is to show you this intertemporal maximization, but it also a bit about to give you an idea of what this micro foundation implies, right? So, I mean, this is a lot of micro, but all this then plays a role in these macro models, right? So, income and substitution effects, right? Think about this, what exactly this was, because this will be very important also for the dynamics that we will see in the macro models later. Good. I think I should probably stop here, and then I'll see you again next week. If you have urgent questions, then we go for 2 more minutes or so. See you next week.
Kommst du auch mit?
Boah, was? Heute am Start. Keine Fortbildung von der Arbeit. So,
Es gibt irgendwie nur noch Grumpy Unit.
was?
Nur noch Grumpy ist das heißt über die
Ja.
Motivation
Aber nehmen wir bei der Arbeit, ne?